All right, you guys, so in this practice assignment that is not graded, we are going to be looking more at t-intervals for matched pairs data and doing some hypothesis tests and confidence intervals for those matched pairs t-distributions. So the first thing we have here is just deciding whether or not we truly have a matched pairs situation. Remember, there are basically three conditions that need to be met to be considered a matched pairs experiment. And that is number one, we need to make sure there's only one variable being measured. So just weight or just height or just exam scores for both samples. Two, we need to make sure two different treatments are being imposed, one treatment for each group, and one of those treatments can and often is a control. In fact, a lot of times the two groups are from the same sample of people. They're measured before and after a treatment is imposed. So the before is basically the control and the after is the treatment. And then the third thing in a matched pairs that is the most important thing about matched pairs is that within the two samples, subjects are matched to other subjects that have very similar characteristics, and we actually list those characteristics usually. So in this first one, it says a school wishes to compare the effectiveness of two math curricula it's developed. The school researchers take two random samples of final math exam scores, one from students who studied the first curriculum and one from students who studied the second curriculum. Researchers then pair these scores based on the grade point average, class, and after-school activities of each student. So is this matched pairs or not? So first thing, is there only one, what is being measured? We should only have one thing being measured. Well, let's see. What they're measuring is exam scores. They're measuring exam scores for both of their samples, so that's good. Two, are two different treatments being imposed, one on each sample? Yes, one is the first curriculum and this other is the second curriculum. So there are two treatments being imposed. Third, are subjects being matched to other subjects in the other sample based on similar characteristics? Yes, it says here, researchers pair these scores based on GPA, class, and after-school activities. So all three conditions have been met. This is a matched pairs study. Okay, part B. A college wants to see if there's a difference in the time it took for last year's class to find a job after graduation and the time it took the class from 5 years ago to find work after graduation. Researchers take a random sample from both classes and then measure the number of days between graduation and first day of employment. So one, is the same thing being measured for both samples? Yes, the number of days between graduation and first day of employment. Two, are there two different two different treatments being imposed? Let's see. Yes, we have last year's class and we have class from 5 years ago. So the treatment is kind of like school today versus school 5 years ago. Okay, so we're comparing the two different classes of education. That's a little bit of a stretch, but okay. The second, though, and the most important, is we need to make sure they are matching subjects based on similar characteristics. There is nothing in this description here, though, that says they're matching people to similar people in the other class. So this is no, because subjects must be paired based on similar characteristics. Okay, and maybe they did that, but they didn't say they did that. So we're going to say nope, characteristics. That is super important. That's also why if you are, like in our previous unit, if you're asked to describe or to create a matched pairs experiment, you have to describe how you are matching your subjects. And you need to list all of the characteristics that you want to be similar. Of course, if you're matching them to themselves, then that's obvious. They're the same person. Okay, part C. In a taste test, a researcher asked people in a random sample to taste a certain brand of spring water and rate it on a scale of 1 to 5. Another random sample of people is asked to taste a different brand and rate it on a same scale. The researcher wants to compare these results. All right, so again, they're scaling things the same way. They have two different sodas, but we don't have any matching. There's no pairs based on similar characteristics. So this is also a no for the same reason as the last one. Okay, and then D, a pharmaceutical company wants to test its new weight loss drug. Before giving the drug to a random sample of people, company researchers take a weight measurement on each person. After a month of using the drug, each person's weight is measured again. Okay, so again, number one, is one thing being measured? Yes, all they're measuring is weight. Two, are there two different treatments being imposed? Yes, they're measuring before and after a drug, a weight loss drug has been taken. So the two treatments are the weight loss drug and the control, no weight loss drug, before they took it. And then the third thing is, are subjects being matched to subjects with similar characteristics? Yes, actually they're being matched themselves in this one. This is a before and after situation, which is a unique type of matched pair situation that actually works really well. People are being matched to themselves. And of course, we all have similar characteristics to ourselves. Okay, for the rest of this, we're going to look at now, we said this first one and this last one are matched pairs. So let's do some analysis, make some inferences based on A and D. So in number 2, it says that the school wishes to, this is about the school and the math curricula. Okay, so they have two different types of curriculum. They call them curriculum A and curriculum B here. And we have students that are matched based on, they said GPA, class, and after school activities. And the students that took A had this score, the students that had B took this score, and so on and so on and so on. So we want to construct, move this down so you can see. We want to construct the null and alternative hypothesis to test whether there's a difference between the final exams for curriculum A and B. So we are going to do a hypothesis test here, I believe, or no, maybe it's a confidence interval. But we got to start with our hypotheses here. So that's all they're asking for at this point. Okay, so my null hypothesis for a matched pairs is always the same. It's always that the mean difference is equal to 0, meaning there is no difference. Okay, in this case, I need to have some subscript here to indicate what this is the mean of. And since they already have a capital A and a capital B here, I'm going to go ahead and leave them like that. So let's go ahead and let the difference be, and actually on the next page, you'll see we're going to calculate B minus A. So I'm not going to do A minus B. I'm going to do B minus A because that's what they have for me on the next page anyways. B minus A. We could also do A minus B. That's not really the point here. Okay, so in context, I also have to write. That would mean that there is no difference in exam scores for groups A and B. Okay, and then our alternative hypothesis would be that there is a difference between the exam scores. For groups A and B. Okay, so how would I write that? Okay, we're not saying one is particularly more than the other. We're just saying that there is a difference. So this is a two-sided test. Okay, moving on then. Now they want us to go ahead and get that data that we need, calculate all of those differences. And I know I showed you how to calculate the differences using the list in your calculator, but we don't necessarily need to do anything with this raw data on the side. The only data we need is the differences themselves. So it's actually, I think, easier to just real quick do 90 minus 83 is 7. Hold on here. 90 minus 83 is 7. 94 minus 90 is 4. 75 minus 78 is -3. Always make sure you're going in the same order. If you get a negative, that's significant. And then just keep going. 78 minus 82. 72 minus 80. And so on and so on. I already have these written down. 1, 2, 3, 0, -3, -2, 4, 1, 1, 2, 5, and 0. Okay. Oop, that should be a 3. My bad. Yeah, 3. Okay. Which, of course, if you go to the next page, hey, look, there's the answers that we just calculated. That was nice of them. So now they're saying, given this following data, create a 95% confidence interval that tests whether there's a difference between the two curricula. So again, in part A, we wrote down our hypotheses that we would use for a two-sided significance test. But remember, a confidence interval can be used in place of a two-sided significance test, and you'll get the same results. So they're asking for a 95% confidence interval, and that's what we're going to do. So the first thing I need is some data. Remember, the confidence interval is going to be X bar plus and minus T star, because we're doing a T interval, or sorry, yeah, a T interval because we don't know the population standard deviation, times S over root N. Okay, so remember, we would use Z star if we knew the population standard deviation, but since we do not, since all we have is a sample, we use a T distribution. So I need to know X bar, I need to know my T star, which is based on degrees of freedom and the tail area, S, and I need to know N. Okay, so I can go ahead and from here, I can calculate my standard deviation and my X bar by hand. It takes forever though. So we're gonna go ahead and use our calculator. And I believe I already have this data in here somewhere. I have a bunch of stuff going on. All right, right here. We just make sure that I have a 3 at the bottom. Okay, good, good. So I'm looking at list 3. I already put the other data in there just because, but we don't really need it. I'll clear that out so it's not confusing. Okay, so I'm just looking at this list 3 data here. That's the data that we just wrote down on the last page and is also right here for us. So I can calculate my 1 var stats to get X bar and S like I need. So I'll go stat, calculate. I wonder if this would help. Oh, hey, it does. 1 var stats, list 3 is where I have my data at the moment. And there we go. So from 1 var stats, I have that X bar is 0.8, S is 3.82-ish, N, of course, is 20 students, or actually there's 40, but they're paired, so there's 20. And then degrees of freedom we're going to need, that's 20 minus 1, which is 19. That's not my 1 var stats, but we find that from 20. All right. So I have almost everything I need. The last thing I need is my T star, which I need the degrees of freedom to find T star. And I also need my tail area. So remembering with a 95% confidence interval, my 2 tails have to be the same and it all has to add up to 100. This is going to be 0.025. But again, grab my on your T table, it does have the confidence levels on the bottom of this particular table, so we don't all actually need the tail area. So we're doing a 95% confidence interval for DF of 19, so we're looking at 2.093. And that is from our table. All right, so that's all that I need to calculate my confidence interval, so I will go ahead and do that. We are calculating here a 95% confidence interval. It's a T interval. So X bar, I wrote this again on the side over here. I'm just going to plug in everything I have now. X bar was 0.8 plus or minus T star times S over the square root of N. So I'll just at this point, you grab out your calculator, start punching in numbers. This margin of error over here ends up being 1.788-ish. So when I subtract, I get my lower bound of my confidence interval. When I add, I get the upper bound of my confidence interval. And just like that, we're all done. So last thing, what can we conclude from this confidence interval? Remember our hypotheses. Our null hypothesis was that the difference was 0. Our alternative hypothesis was that the difference was not 0. Okay, and when we were doing a significance test, which is basically what we are trying to accomplish with this confidence interval, we are trying to either reject or not reject this. So can I reject that the difference is 0? No, 0 is in this interval. So we cannot reject the possibility that 0 is the true mean difference. So my conclusion is we cannot reject H naught, which was that there is no difference in exam scores. Always put your context in your conclusions. So we cannot reject H naught, the fact that there's no difference in exam scores for groups A's and B, because 0 is in our 95% confidence interval. For the true population difference. So again, with these confidence intervals, this confidence interval, when we write this, we are saying we are 95% confident the true population mean, which in this case the population mean of differences, is within these two numbers. And since 0 is within these two numbers, we can't rule out that it's not, that it is possible. Okay, so we're saying there's really not a significant difference between these two curriculum. All right, next scenario. Let's look at our pharmaceutical company. So here's our data for our pharmaceutical company with their weight loss drug. We are first going to do the same thing. We're going to set up our null and alternative hypothesis that would allow the company test its drug for effective weight loss. So again, our null hypothesis is that the difference is 0. Okay, and what is my subscript going to be here? There's no labeling here. When I look at afterwards, I can see later on we're just gonna call this after minus before. So I know I'm gonna do after minus before. When I just label these with A and B's, A minus B. So that would mean that A is after and B is before. So I'll say A minus B, because looking ahead, I can see we're gonna do A minus B. So it would not be helpful to do B minus A. Okay, so the mean of A minus B is equal to 0. In context, that means there's no difference after taking the weight loss drug. Or the weight loss drug makes no difference in weight loss. Or the weight loss drug is not effective for weight loss. Is not effective. Okay, and then our alternative hypothesis, what we are hoping for here is that it is effective. Ooh, I need to zoom out for you. Bloop. There you go. All right, so let's see. If it is effective, then that would mean they would weigh less after than before. So if they weigh less after than before, and I do A minus B, the after weight, minus the before weight, will we get a positive number or a negative number? We would get a negative number. The weight would go down. So the after weight should be less than the before weight. So all of these numbers we are hoping are going to be negative numbers. So my alternative hypothesis is that we are less The difference is less than 0. The difference is negative because the weight is going down. So that in context, we would say the weight loss drug is effective. All right, moving on. Okay, in this next part, we're going to talk about how we can do this kind of stuff with our calculator. All right, so the first thing I need here is I need all of my differences. That's the actual data I'm going to use in my tests or intervals. So I'm going to write those down real quick, looking ahead. It's not written for me anywhere. So I'll just subtract. We're doing after minus before, so I have to make sure I go in the correct order each time. If I have a negative or a positive, that is super important that I write them down correctly. So 180 minus 185 is a negative 5. This is a negative 4. Whoops. Negative 3. Here I get a positive 3. I might even write a plus sign just so that I don't mess that up. There's a 0. This is a positive 2. Negative 10. Negative 7. Positive 4. Negative 6. 0, negative 2, negative 3, negative 8, negative 5, negative 8, negative 6, positive 2, negative 9, and lastly, big loser, negative 10. All right. So now that I've got all that all done, it says, what test would you use to determine whether there's a significance difference between the before and after weights? So we're doing a whole significance test here. We checked our conditions. Oh, we didn't check our conditions. Let's check our conditions. We can't do any kind of a test until we've checked our conditions. For a T interval, we need to have either a large sample, greater than 30. This is not 30. Or since it's a small sample, we will need to check for outliers and extreme skewness. So let's see here in my lists. I believe I have this. Yes, I do. Okay, I have my list already in here. I put it in L6 a while back. So let's go ahead and check real quick for skewness and outliers. The easiest, quickest way to do that check is with a modified box plots. So I'm in L6. I already have modified box plot selected. This oversays does not glare. L6 graph. Ooh, I got lots of things going on here. Hold on here. Get that out of the way real quick. All right, I got rid of that sketch of that T distribution just by adjusting my window or my zoom real quick. So zoom 9 here is my box plot. I can see there is no dots on either side, so there's no outliers. And this looks mostly symmetrical. So I'm going to sketch it on here to kind of show my work. Looks kind of like that. So there's no extreme skewness. It's not perfectly symmetrical, but there's no extreme skewness or outliers. So even with a small sample, that is efficient enough to use a T distribution, which means I can do a T test. And since we have 2 samples here, we are actually going to perform a, it's actually just a regular T test. I'm getting ahead of myself. We will perform a T test at alpha equals 0.05. And it says, why? Why are we doing a T test? Meaning, why are we not doing a Z test? Why do we ever do a T test instead of a Z test? Z tests are better. We do T tests more often, actually, in real life, because we don't know the population standard deviation. So I'll say because we do not know sigma. Okay. And moving on now, it says perform the t-test on differences after minus before that you calculated in step B. Boom, done. So, and they give you the directions here for a TI 83 or 84. And then on the back page, they give you the directions for a TI 89 as well. I don't think any of you guys have a TI 89. I, of course, have a TI 84. So we'll go through this here. So we go stat, option 1, enter the numbers in. I already did that, but I did not use L1. I used L6. Oh well. Double check your numbers, of course, as always. Press the stat button again. Stat. Move over to tests. There's tests. And you can see we got t-tests, and we also, you see that 2 sample t-tests? We're not there yet. That's the next section. Okay, we're doing a t-test, is a regular t-test, 1 sample. Okay, I know there's 2 samples up here, but we're only using this. We're basically acting like this is our 1 sample. Okay, so it's just a regular t-test, enter. And we can do this one of 2 ways, okay? I could hit stats and put in the stats that we can calculate using our 1 var stats, or I can go data, which I'm going to do because I have not calculated my 1 var stats yet, and then just tell it to get the data from list 6. Okay, so mu sub 0, that's our null hypothesis, of course, is that it is 0. The difference is 0. Our data is in list 6. No frequency. This is we wanted the data to be less than. Yeah, it was less than, wasn't it? Yeah, we wanted negative numbers, so this is a less than situation. Less than 0. And then I can calculate or draw. Draw gives you a nice, great picture, but it doesn't give you quite as much numbers. So depending on what you want, you can look at both. I'm going to hit calculate, and it gives me all the information that I have here. So it shows us our alternative hypothesis is that the mean is less than 0, negative, which is what we wanted when we're losing weight. Our T, our T variable is negative 3.80. I'm writing this down, but you can't see it. My p-value, the probability of t being less than that, is right here. And again, this e negative 4 means I'm going to take that decimal and move it 4 spaces to the left, so it becomes 0.0006. So is that less than our alpha? Absolutely, it is less than alpha. So we can reject our null, which is the last part of this. We reject H naught because P is less than alpha. Yeah, let's put that in context though. Since 0.0006 is less than our significance level, 0.05, we have enough evidence to support our alternative hypothesis, which says that the weight loss drug is effective. So now you know when you see those advertisements for weight loss supplements and weight loss programs, and if you do some research on them, you'll see things like this has not been proven to be effective, or this has been proven to be effective. You can look into how they analyze that data and determine, like, you know, is that really true or not? Maybe they used a significance level that was like really big. That obviously would skew your data. There are definitely ways that we can manipulate our statistics to make it look like something is a certain way. And without knowing anything about statistics, it's very easy to kind of fall into that trap. Anyways, this is it for 3.2. I'll see you later.